続いては、ウェイチー・チャオさんによるCryfind、バイナリ中の暗号化アルゴリズムを識別するツールとして動画をご紹介いただきます。ウェイさんは台湾のサイクラフトのインターンとして活躍。バンブーフォックスチームに属する CTF プレイヤーであり、2019年のデフコン CTF では BFS チームの一員として参加された方です。それでは今回のテーマについて動画をご覧ください。ご覧いただいている間ですね。
Hello everyone, my name is Weijie Zhao, and today I'm going to talk about how I build a static analysis tool to identify cryptography algorithm in binary. And our main goal is to automatically identify cryptography algorithm in binary, and we want to use static signature-based analysis. And because cryptography is a widely used features in malware, so for some malware, encryption is one of their main activities. For example, ransomware encrypt victim file and ask for money. To resist security researchers' analysis, malware often change rapidly, but cryptography algorithm scheme is most caused to change. Our goal here is to provide an automated tool to identify cryptography algorithm used in binary. We want to do it in static signature-based analysis, which is more efficient and general than dynamic techniques, and therefore more scalable in real-world application. After some research, we found that there are three main strategies people use to solve this kind of problem. And first is signature-based approach, which is the most common one. This method searches for cryptography concerning binary. And the second method is to collect a lot of cryptography algorithm and build an assembly code pattern database and do pattern matching. The difficulty in this method is to collect enough cryptography algorithm and build the pattern, and also that a simple optimization may easily break it. And the third method is the data flow graph isomorphism. It compares the similarity between data flow graph of the target and database. This method is hard to implement and may be less efficient. So after various consideration, we thought signature-based approach is most easy to implement and most efficient among all. And it also can achieve great result. And here's our main strategy. And below is an example of the SHA-1 initial array and ADV API 32 DLL library. And cryptography concerns are often quite unique with few false positives. Therefore, it is a strong evidence of the existence of a cryptography algorithm. If malware chooses to implement it, cryptography algorithm by themselves, we can search for cryptography constant in binary. But some malware may choose to use existed cryptography library. That's why we also search for cryptography API names in binary. And there are some static signature-based analysis tool already be implemented by other tools. Some are PE executable and some are plugin for reverse engineering framework. These tools are either slow or incomplete. So we want to build a faster and more complete tool. And we start by collecting crypto constant from this tool and many sources. But not all of them are open source. So we need to do some reverse engineering to get the cryptography constant inside. And after we collect lots of cryptography constants, we try to find them in sample cryptography algorithm implementation and testing whether we have collected enough cryptography constant. But we fail to find the constant in MD5 sample implementation. So let's try to find out why it's not working. So let's look at the source code of the MD5 sample implementation. And you can see here the cryptography constants are indeed in the source code. And also in our cryptography constant database. So both constants are there. Then why are the cryptography constant can be found in the binary? So looking at the assembly code, we can find out that the addition has become subtraction because the value is also negated in 2's complement in 2's complement representation. So that's why we can find the cryptography constant in binary, because it's been negated. So we need to do some encoding method in order to find the previous example. So we try to consider various encoding methods on the cryptography constants, including the big endian, little endian, and their combination with negation in 2's complement. And each group of constants also have different size, like forward, D word, and Q word. D words stand for 4 bytes, and Q words is 8 bytes. So for example, base 64 table is stored in forward, and all the bytes are contiguous. On the other hand, the SHA-1 initial array is a group of constants with size D word, and so they may be scattered apart. So we need to search for them independently, each of the constant independently. And while we search for the constant, each constant independently, we may encounter some false positive case. In this example, the first constant appears a lot in the binary file, and the other constant only have few occurrence. So 1111 happens to appear many times in here. But actually, there should be only one group of constant. Like the highlighted section, we only have one group of constant. So how do we pick up the correct group of constant? At the beginning, we only have addresses where the constant appear, and we want to find the smallest interval that include all constants. And given an interval size, we can easily scan the address to check if it includes all constants. So we can do a binary search on the interval size, and then we are done. And after we found the match, we can pull the constant out and do the same thing on the remaining constants. And notice that we restrict the interval size to be no more than one page size, because we assume that the constants are not very far, very scattered, that it may be scattered only in a page size. Okay, so next we compare several implementations to test which method is better to search for constant in binary. And first we use Python built-in operator for the baseline. Then, since we search for multiple constants in the same binary file, we consider using the AC algorithm, which has better time complexity than the baseline approach. And finally, we consider using the Yara rule engine to do the searching part, do the work for us. So after some experiment comparing with various sizes of the sample, and Yara rule has the best performance among all. And therefore we choose Yara rule engine as our main strategy to search for constant in a binary. And using the Yara rule engine, here is the example of our tool to export the Yara rule generated Yara rules. And you can see that it's actually just combinations of different encoding and size. Simple data obfuscation techniques to XORing a secret key on a sequence of bytes. So we try to deal with this case. And one simple solution is to try out all the 256 possible keys, but this will cause a significant loss in performance since we are doing the same search for 256 times. So instead, we XORing the JSON bytes of the signature and also the binary to form XOR difference arrays. And then we simply search in this XOR difference array. And after we found a match, we can check for the correctness, and we are done. So This method can also easily to extend it to longer key lengths longer than 1. And for example, if we have signature 3, 5, and 7, and we have binary which have this signature, but the signature is XOR with 2. And 3 is XORing with 2, and 5 is also XORing with 2, and 7 is also XORing with 2. We can find them with normal search. But if we XOR in the adjacent bytes, then the signature becomes 6 and 2, and the binary becomes 6 and 2 and 1. And we see that the 6 and 2 appears. So we can simply search in this XOR difference array, and we can find the signature in the binary. Okay, we can easily extend this XORing trick to longer key lengths. In this example, the binary is encrypted with XOR key 2 and 3, which has key length of 2. And we can calculate the XOR difference array again. But this time, we XOR in the bytes which are 2 bytes apart. So 3 and 7 in signature is XOR, and the result is 4. And also the 5 and 4 is XOR, and the result is 1. We can do the same thing in a binary. We XOR the 3 XOR 2 with 7 XOR 2. And the 2 is cancelling out, and we get 4. And also, we can XOR 5 XOR 3 with 4 XOR 3. And the 3 is cancelling out, and we get 1. Therefore, we can find the signature 3, 4, 5, 7, 4 in the binary, even if they have been XORed. In our tool Cryfind, we have implemented this algorithm with arbitrary key lengths. So you can try many different key lengths in the sample binary. But notice that if you use larger key lengths, your signature also need to be larger. Otherwise, after calculating the XOR difference array, it will be too short. And besides searching in a binary, we also do emulation using RADIATO framework. And first, we pull out all the functions, and then we build a spanning tree on the function control flow graph to avoid cycle. And then we emulate each path and dump the stake. Finally, we search in the stake for cryptography constant, like we do before. And then doing this can help us defeat some simple data obfuscation technique which assemble the value in runtime. So in conclusion, our main strategy is searching cryptography constant in binary using our engine, and consider different encoding methods and different size. Then we implement custom algorithm to bypass simple data obfuscation technique efficiently, such as the XORing trick and the emulation. And here is the demo of our tool, Cryfind. And in this example, we use shadow hammer as our target. And as you can see, we successfully found a constant, which is a custom decoder used by Winty family a lot. you can see that this constant is encoding with two different encoding methods. One is the big endian, the other is the negation part. And our tool can successfully locate the constant in this malware. Okay, so next we're comparing the speed with other tools, and we use the 3 MB sample binary with a size of 3 MB, and our tool use only 0.89 seconds to analyze the binary, and while other tools need more than 2 seconds to do that. So we are better in performance against other tools. As for the cryptography signatures, our tool also has larger collections than other tools. Despite we restrict ourselves to static signature-based approach, we can also consider slower and heavier dynamic analysis approach. You will need more time, but may find more robust evidence of a cryptography algorithm. Most of the previous research compare and analyze extractive loops. Because loops are important part in cryptography algorithm. Most of the cryptography algorithm use a lot of loops, and it's a crucial part in the cryptography algorithm. We suggest there are 3 possible ways of doing this. One is to study the input-output relationship comparing to sample cryptography implementation. And the other method is to do a symbolic execution on the loops, which may be very heavyweight, but may find more robust evidence of the loops of the cryptography algorithm. And the third method is to use machine learning to classify the loops into different algorithm. And we will do some more research on this method in the future. Okay, so that's it. Thanks for listening.